Welcome to a space where ideas spark curiosity, questions ignite answers, and inspiration transforms lives. This is Mind Alchemy, your destination for unlocking potential in everyday life. Welcome to this Weka tutorial. We'll dive deeper into two key terms I've used in previous videos, the training set and the testing set. So, what are these terms and why are they important? These concepts are critical for evaluating the robustness of a machine learning model. Let's start with the training set. As I've mentioned before, the training set is used to teach the model. It helps the model learn the patterns and relationships within the data. Once the model is trained, if we provide it with similar data that lacks predefined labels, the model should be able to predict the correct class or category for that data. This prediction is then tested using the testing set, which ensures the model can generalize well to unseen data. I am demonstrating how to check the robustness of a model. Primarily, we begin by working with an entire dataset. As I've shown previously, this involves loading the dataset, and here I'll do the same. For this demonstration, I'll open the social media advertisement dataset, which I have used in earlier examples. Now, with this dataset, let's consider how it can be divided into a training set and a testing set. This dataset contains labeled data, where decisions are already provided as yes or no. To train the model, I'll use a portion of this data with the labels provided. The remaining portion of the data will serve as the testing set, where I won't provide the labels to the model. The model will then predict labels for the testing data, and I can compare its predictions against the actual labels to evaluate its performance. This approach allows us to assess whether the model is accurately identifying patterns and making correct predictions, ultimately testing its robustness. Let's explore how we can validate a model. There are three main techniques for this process: k-fold cross-validation, train test, split, and manual division into training and testing sets. Additionally, there is another method, leave one out cross-validation, which isn't officially supported by Weka, but can still be implemented manually. Suppose we have a dataset with 400 rows and 4 columns, giving it dimensions of 400 by 4. Here, k represents the number of folds. If we set k equals 5, the data will be divided into 5 equal parts, or folds. Each fold will then contain 400 divided by 5 is equal to 80 rows of data. During the first iteration, the process works as follows. Fold 1 will act as the test data, containing 80 rows. The remaining folds, fold 2, fold 3, fold 4, and fold 5, will serve as the training data, totaling 320 rows. In the second iteration, fold 2 becomes the test data, while fold 1, fold 3, fold 4, and fold 5 form the training data. This process continues until each fold has been used once as the test set, resulting in 5 iterations as k equals 5. If k is set to 10, there will be 10 iterations, with each fold being used as the test set once. Next is train test split. This is a simpler approach where the dataset is divided into 2 separate parts. Training set, used to train the model. Testing set, used to evaluate the model's performance. Leave one out cross-validation method is a specific case of k-fold cross-validation, where k equals the total number of data points. Essentially, each data point is treated as a separate test set, while the remaining points form the training set. By understanding these methods, we can ensure a robust evaluation of machine learning models, improving their accuracy and reliability. Let's walk through the process step by step. First, I'll demonstrate how to select the file for our analysis. Navigate to the location of the dataset, in this case on the desktop. Once there, choose the CSV file. For this example, we are using the social network dataset, setting up the classifier. 1. After loading the dataset, I'll select the meta classifier option. 2. From the meta classifier, I'll choose the filtered classifier. 3. Within the filtered classifier, I'll select random forest as the learning algorithm. Random forest can be found under the trees category. Configuring the random forest classifier. Once random forest is selected, I'll configure its parameters. Since this is an imbalanced dataset, I'll use the class balancer filter to ensure better decision making. After selecting the class balancer, click OK to confirm the settings. Let's observe how the accuracy changes with different values of k in cross-validation. For a 5-fold cross-validation, the accuracy achieved is 89.5%. However, when we increase k to 10, a 10-fold cross-validation, the accuracy changes slightly to 88.5%. This variation highlights the sensitivity of model evaluation to the choice of k in cross-validation. Larger values of COF k provide a more granular assessment by dividing the data into smaller test sets, but the overall pattern of accuracy may shift slightly depending on the dataset and model. Now, if we provide the value of k as 400, the process runs for all the 400 instances. During this, the model evaluates one fold as the test set, while the remaining folds serve as the training set. The accuracy for each iteration is displayed, and by the end, you will have the results for all 400 instances. This method is known as leave one out cross-validation. In this scenario, only one instance serves as the test data, while the model is trained on all the other data points. This process is repeated for each instance, making it more exhaustive, but also more computationally intensive. The accuracy in this case is 89%. Now, if I set a percentage split, for example, 80%, it means 80% of the dataset will be used for training, and the remaining 20% will serve as the testing set. To clarify, 80% of 400 data points is 320. This means that 320 instances are used for training. The software will automatically select the training set, and the remaining 20%, or 80 instances, will be used for testing. In this case, the result for the train-test split is 93.75%. This accuracy corresponds to the testing set, which consists of the 80 data points not included in the training set. Another approach I can use is manually setting the training and testing datasets. To demonstrate this, I'll first open the file that contains the training data, which I've already divided. This is the training data, and as you can see, it has been manually prepared rather than generated by the machine. Now, I will manually define the testing data. This test set has been user-defined, meaning I have selected the data for testing. After selecting the test set, I can begin the classification process. Once the classification is complete, the results are displayed. As you can see, these results are from two different methods, one automated and the other manually configured. While the overall accuracy may be similar, the confusion matrices reveal slight differences. For example, in the first case, the results show 47 correct predictions for no and 28 for yes. In the second case, the results are 58 for no and 17 for yes. Although the final accuracy may be similar, the distribution of correct and incorrect predictions can vary between the methods. If you found this tutorial helpful, like this video, subscribe for more AI tips, and share it with a friend. Check the description for links to our Udemy course for automating your daily tasks with generative AI, and I'll see you in the next video.